Dear students, welcome back to video classes. In the last session, we discussed complement of a set, problems to find complements of given sets, right? And also we discussed properties of complement of sets, right? Today, we are going to discuss some important results or formulas, and later we are going to discuss practical problems based on those results, okay? Before that, you just make a note of this. Note A minus B is equal to A intersection B dash. For any two sets A and B, A minus B is equal to A intersection B dash. I'm not going to prove this result. You can easily verify this result through drawing Venn diagrams, okay? This result is very useful in the chapter probability theory, okay? So just make a note of this. For any two sets A and B, A minus B is A intersection B dash, okay? Now we shall move on to important results. Result number one, let A and B be two finite sets. Let A and B be two finite sets such that A intersection B is equal to null set. That means A and B are two disjoint sets. Then n of A union B is equal to n of A plus n of B. Result number one, let A and B be two finite sets such that A intersection B is null set. Then n of A union B is equal to n of A plus n of B. That means number of elements present in the set A union B is equal to number of elements present in set A plus number of elements present in set B. Proof is very obvious from the Venn diagram. Here A and B are two disjoint sets. Okay. So the shaded region represents the set A and B. Number of elements present in the shaded region or in the set A and B is the sum of the number of elements present in set A and set B. Okay. Proof is obvious from the Venn diagram. Proof is very clear from the Venn diagram. Result number two, let A and B be two finite sets. Then n of A union B is equal to n of A plus n of B minus n of A intersection. Now we shall prove this result. Proof. First we shall draw the diagram. The first circle represents set A, second circle represents set B. Okay. This shaded region represents the set A minus B. This shaded region represents B minus A. And this common region represents A intersection, right? See, clearly these three sets, A minus B, A intersection B, and B minus A are mutually disjoint sets. Mutually disjoint means intersection of first and second is null set. Intersection of second and third set is null set. Intersection of first and third sets is null set. And the union of these three sets is nothing but the set A union B, right? Proof. the sets A minus B, A intersection B, B minus A are pairwise disjoint, and their union is the set A union B. These three sets are pairwise disjoint sets, and their union is equal to A union B. Therefore, n of A union B. Therefore, number of elements present in the set A union B is number of elements in the set A minus B plus number of elements in the set A intersection B plus number of elements in the set B minus B. So, n of A union B is equal to n of A minus B plus n of A intersection B plus n of B minus A. Okay. Now, I will rewrite the right hand side like this: n of A minus B plus n of A intersection B. I'll just write these two terms within brackets plus. Now, here I'll just add and subtract this by n of A intersection B, n of B minus A plus n of A intersection B minus n of A intersection B. I have just added and subtracted right hand side by n of A intersection B. Now this is equal to, and now you just observe here the sets A minus B and A intersection B. These two sets are disjoint sets, and their union is the set A. Therefore, sum of the number of elements in A minus B and number of elements in A intersection B, this sum must be equal to number of elements in set A, right? Similarly, see the second bracket here. The set B minus A and the set A intersection B, these two are disjoint sets, and their union is set B. Therefore, sum of these two must be n of B, right? And minus n of A intersection B. So therefore, n of A and B is equal to n of A plus n of B minus n of A intersection B. Okay, this is a very important result. In the final examination, you will have a problem on this result. Okay, next, result number 3. Let A, B and C be three finite sets. Let A, B and C be three finite sets, then n of A union B union C, number of elements present in the set A union B union C is equal to n of A plus n of B plus n of C minus n of A intersection B minus n of B intersection C minus n of A intersection C plus n of A intersection B intersection C. So this is result number 3. Let A, B and C be three finite sets, then n of A and B and C is equal to n of A plus n of B plus n of C minus n of A intersection B minus n of B intersection C minus n of A intersection C plus n of A intersection B intersection C. Okay, I'm not going to prove this result. If you want, you can prove this using result number 2. Okay, next, result number 4. Let A and B be two finite sets. then let A and B be two finite sets, then n of A minus B, then n of A minus B, number of elements present in the set A minus B is equal to n of A minus n of A intersection B. Okay, n of A minus B is equal to n of A minus n of A intersection B. Okay, proof is very simple, so I'm not going to prove this. Proof is similar to the result number, proof of the result number 2. Okay, just one more, fifth one. Let U be the universal set and A be a subset of U. Then n of complement of A, then n of complement of A is equal to n of U minus n of A. Number of elements present in the complement of the set A is equal to number of elements present in the universal set minus number of elements present in the set A. Okay, so here also you can easily prove this result. I'm going to prove the result number 5. We know that A union A dash, we know that union of any set A and its complement is equal to universal set, right? So n of A union A dash is equal to n of U. N of A union A dash is equal to n of U, right? And further, we know that A and A dash are disjoint sets. A and A dash are disjoint sets. So that means using result number 1, left hand side can be written as n of A plus n of A dash, right, is equal to n of U. Since A and A dash are disjoint sets, we can use result number 1. So this implies n of A dash is equal to, this implies n of A dash is equal to n of U minus n of A. Okay. Number of elements present in the complement of set A is equal to number of elements present in the universal set minus number of elements present in the set A. Okay. So these are the important results. Now we are going to discuss some practical problems based on these results. Okay. First problem: if X and Y are two sets such that X union Y has 50 elements, set X has 28 elements, set Y has 32 elements. The question is, how many elements does the set X intersection Y have? Okay. So what is given here? Set X union Y has 50 elements. So we shall write it as n of X union Y is 50. Set X has 28 elements. So n of X is equal to 28. Set Y has 32 elements. So n of Y is equal to 32. The question is, what is the number of elements in the set? What is the number of elements in the set X intersection Y, right? So use the result number 2. N of X union Y is equal to n of X plus n of Y minus n of X intersection Y. This is result number 2. Now substitute the values. So this will be 50, right, is equal to 28 plus 32 minus n of x intersection y. Now we shall shift this to left side. Therefore, n of x intersection y is equal to 28 plus 32, 60. Shift this to right side. 60 minus 50, 10. Therefore, the set x intersection y has 10 elements, right? Problem number 2. If x and y are two sets such that n of x is 17, that means set x has 17 elements. Similarly, n of y is 23, the set y has 23 elements. N of x union y is 38, that means the set x union y has 38 elements. The question is, what is the number of elements in the set x intersection y? So use result number 2. So write that formula, n of x union y is equal to n of x plus n of y minus n of x intersection y. Okay, so what is n of x union y? It's given 38, n of x 17 plus n of y 23 minus n of x intersection y. So now shift this to left side. So n of x intersection y is equal to 40 minus 38, which is equal to 2. Therefore, the number of elements present in the set x intersection y is equal to 2, right? Fine. Okay. Question number 3, problem number 3. In a class of 35 students, 24 like to play cricket and 16 like to play football. Also, each student likes to play at least one of the two games. How many students like to play both cricket and football? Okay. Now we shall solve this problem. We shall take C as a set of students who like to play cricket and F as a set of students who like to play football. Okay. Let C denote the set of students who like to play cricket. And capital letter F denote. Let F denote the set of students who like to play football. Okay. C denotes set of students who like to play cricket. F denotes set of students who like to play football. Now, it is given that 24 students like to play cricket. So, n of C is equal to 24. It is given that 16 students like to play football. So, n of F is equal to 16. Next. And also it is given that each student likes to play at least one of the two games. Therefore, we have to take n of C union F is equal to 35. In this problem, the set C union F is same as universal set because there is no one left in the set of students. Okay. There is no one who doesn't play any game. Okay. So here in this case, C union F is same as universal set. So n of C union F is equal to 35. The question is, how many students like to play both cricket and football? So what is n of C intersection F? This is the question. what is n of C intersection F, right? So now write the result number 2. So result number 2, n of C union F is equal to n of C plus n of F minus n of C intersection F. Substitute the values. N of C union F is 35, n of C is 24, n of F is 16, minus n of C intersection F. Simplify this further, shift this to left side, n of C intersection F is equal to 40 minus 35 is 5. So conclusion, therefore, the number of students who like to play both cricket and football is 5. So write a conclusion, that is, the number of students who like to play both cricket and football. Both cricket and football is 5. Right. Next one. Next, problem number 4. In a committee, 50 people speak French, 20 speak Spanish, 10 speak both Spanish and French, and each speaks at least one of the two languages. Okay. How many speak at least one of these two languages? That's a question. Okay. So let us take F as the set of people who speak French, and capital letter S as the set of people who speak Spanish. Okay. Let F denote the set. Let F denote the set of people who speak French. Let S denote the set of people who speak Spanish. Now, what is N of F? Number of people who speak French is 50. Number of people who speak French is 50. Next. N of yes, number of people who speak Spanish is 20. And after that, 10 speak both Spanish and French. So N of F intersection F is 10. In the committee, each one speaks at least one of the two languages. The question is, how many speak at least one of the two languages? So that is N of F union S. N of F union S. N of F union S. So write the formula, substitute the values. So what is the formula? N of F union S is equal to N of F plus N of S minus N of F intersection S. Substitute the values. N of F is 50 plus N of S is 20 minus N of F intersection S is 10. F union S is the set of those people who speaks either French or Spanish or both. Okay, or in other words, this is a set of people who speaks at least one of the two languages. Okay, after simplification, we get 70 minus 10, 60. That means the number of people who speak at least one of the two languages is 60. Okay. Question number 5. Problem number 5. In a group of 65 people, 40 like cricket, 10 like both cricket and tennis. Also, each person likes at least one of the games. How many like tennis only and not cricket? How many like tennis? There are two questions here. Okay. We shall take C as a set of people who like to play cricket and T as a set of people who like to play tennis. Let C denote a set of people who like to play or who like cricket, and capital letter T denote the set of people who like tennis. Okay, so N of C is equal to 40. N of T is equal to, this we don't know, this we had to find out. N of C intersection T, 10 like both cricket and tennis, so this must be 10. Okay, there are 65 people. It is given that at least one of them, each person likes at least one of the games. Therefore, 65 must be N of C union T. Okay, 65 is equal to N of C union T. The first question, how many like tennis but not cricket? Second question, how many like tennis? First, we shall find the answer to the second question. We shall find out N of T. Okay. So, use the result number 2. N of C union T is equal to N of C plus N of T minus N of C intersection T. Now substitute the values. N of C union T is 65. N of C 40 plus N of T that we don't know, write that as it is. N of C intersection T is 10. So shift this to left side. So we get 35 is still N of T. N of T is equal to 35. That means that is the number of people who like tennis is 35. We have answered the second question. Now we shall answer the first question. What is the first question? We had to find number of people who like tennis but not cricket. So how do you write that? N of number of people who like tennis but not cricket. N of t minus c. So use result number 4. Use result number 4. This is nothing but n of t minus n of c intersection t. What is n of t? Just now we have found out. N of t is 35 minus number of people who like both cricket and tennis is 10. So this is equal to 25. That means that is the number of people, who like tennis but not cricket. This is 25. Okay. This is the answer to the first question and this is the answer to the second question. That's all for now. We shall continue the next class. Okay. So thanks for watching the video.